Well, Dave's talked about excitement. I feel that excitement. I think you guys are starting to share that excitement with me. I've been working on this program for 9 years, so you can imagine this has been my dedicated effort for 9 years. The only thing I compare right now to is being an expectant father. Is that the right term? You know, anticipation is just so big. The problem is it makes expectant father is just a nervous wreck. So that's sort of the way I feel right now. It's a very exciting time, and I'm glad you're all here to share that moment and to share it with the nation. But in that process, to share the excitement of what's to come with this satellite. I'd like to start off just a little bit about, our history. We know that the polar satellites were first started in 1960. The low Earth orbit, where people recognize that, and that was a valuable satellite early in those days. In the mid-'70s, NASA decided to try putting a camera on a geostationary satellite and seeing what that was like. Well, the first images that came back from that geostationary satellite set the weather community on fire, because instead of getting photos every hour and a half of what's going on, they're getting images that were capturing what's happening right now from the same location. And the cry was, give us one of those operationally. So after a very quick demo, NOAA then built the first GOES, which was launched in 1975 as a spinner satellite. GOES 4 through 7, we did add the vertical profiler about 1980. And then in the 80s, we worked on switching the satellite from a spinner to a 3-axis stabilized. So instead of having to deal with your instruments, which were always turning, which affects their ability to focus on the Earth, you had a nice stable platform with an Earth-pointing platform that you could put your instruments on to stare at the Earth. You have a little bit better performance in the instruments. Now, in this time, through the 70s, 80s, and 90s, we really didn't add a lot of capability into it. When we built the current series, NOMP, which are now 13, 14, and 15, and launched them starting in 2006, we've really only added some improved sensitivity and a couple channels over that time. So when we look here in 2016 is what the GOES-R is, we are not only redoing the whole system, but we're infusing a technological leap that has never been seen in the entire program. I would say it's on the order of what we saw when we first saw those first geostationary images way back in the 1970s. So that's why we're very, very excited in terms of the technological leap. Some forecasters I've talked to, some of the older folks like myself, are regretting the fact that they're nearing retirement. They wish they're just coming out of school, because they know this is like a once-in-a-career bump up in capability that they would love to have spent a career exploiting and using in the forecast process. Looking at our configuration, Joe did show this, but right now we've got GOES East and West, 13 and 15 operation with 14 in storage. So we're in a very healthy situation as we launch GOES-R. Everyone wants to know the answer to the question, where thou wouldst go, GOES-R. So I'll be taking little bets here. We'll have an East and a West pool if you want even money on that, either one of those. I tell you, I'll hold the money until we do, right? So the point is, we really are excited about GOES-R. The community's very excited about GOES-R. And those of us on the satellite side know that I can't, if it was just another of the older satellites, we'd just launch it and put it in storage. But the hue and cry has been so great from the community that we know that we can never turn it off once we launch it. So to get around the idea of storage, we are going to be testing it out for a full year with the expectation at that point we'll make the determination whether it goes east or west. And then we'll have GOES-S come along in early 18, and we'll get that out in the other orbit. So certainly by late 18, we'll have the full GOES-R capability east and west. With the older satellites, that's the question. How long we fly them versus flying the new ones will unfold. But clearly, I think the louder the community cries for the new capability, the quicker they'll all get into orbit. So you got your assignments, right? You will always say more, more, more. That's keeps us satellite folks busy. Just from a background, we got a number of experts. Usually when I give these talks, I get to talk about all the eye candy. Dave, calls me the eye candy master, but I don't get to show any of that today. We got the experts, the scientific experts, as opposed to the engineers talking about that. So I'll just give a slight overview. As you know, we're continuing the imager. We're introducing a new lightning mapper. We're continuing the in-situ measurements with the electron and ion sensor, as well as the magnetometer, which capabilities are flying today. And then for the sun staring telescopes, the EXIS and SUVI are follow-ons to what's flying today. So for this briefing, I'm just going to step through and introduce those systems, and we'll hear from the experts how they're going to be used. Now, since I'm talking so much this week, my staff gave me a break and let me put some videos in here. So
Weather
this is just
is always changing, and the better we can predict what's coming, the better we can prepare. The GOES-R series, NOAA's next-generation geostationary weather satellites, will be a game-changer for weather forecasting. For the first time, GOES-R, which will be called GOES-16 once it's operational in space, will be able to monitor the Earth in near real time. Using a powerful new instrument called the Advanced Baseline Imager, GOES-R gathers data and imagery about weather over the Western Hemisphere as frequently as every 30 seconds. This enables NOAA to gather data with 3 times more channels, 4 times better resolution, 5 times faster than before. Faster, more accurate data means better observations of phenomena like severe storms, fire, smoke, aerosols, and volcanic ash. But this is not the only new instrument aboard the satellite. GOES-R is flying another powerful technology called the Geostationary Lightning Mapper. This instrument can not only measure when lightning strikes the ground, but also lightning activity in the clouds that is charging the atmosphere. Researchers have found that an increase in lightning activity may be a sign that tornadoes will form. GLM will change the way forecasters look at severe weather to provide faster and more accurate warnings. All of this new technology means forecasters at NOAA's National Weather Service will have valuable tools to improve predictions of severe weather events, like hurricanes, providing faster warnings to emergency managers to help save lives and protect communities. Space weather is serious business in the 21st century, as much of modern life relies on sophisticated electronic systems. Working with other NOAA satellites, GOES-R will observe space weather with a suite of instruments that collect information about radiation hazards from the sun. Space weather can interfere with communications and navigation systems, damage satellite electrical systems, cause risks to astronauts, and threaten power utilities. NOAA launched its first geostationary satellite more than 40 years ago. Since then, the invaluable data from GOES satellites has been essential to countless industries like aviation, sea transport, and communications that rely on weather data. Sitting 22,300 miles above the Earth, the advanced technologies flying on the GOES-R series of satellites take weather forecasting to new heights.
Wow. The GOES-R 101. I did put that out there because we've got a lot of great videos and snaps and a lot of detail on our YouTube channel and our website. So the idea is if any of that is of use to you, please use it in your pieces. From the GOES-R system architecture, I just want to let you know the big thing here is the ABI, because of its increased capability, really drove our entire system. Basically, the data rate is an order of magnitude greater than today's GOES. And what that forced us to do is basically replace the entire infrastructure of the current GOES system. So while the on-orbit architecture will look the same, we did replace all of the hardware and antennas here at NSOF as well as out at Wallops where the data comes down. And for geographic diversity, we had to put in a backup system out at Fairmont, West Virginia. so that if a hurricane or something threatened Wallops, we could still operate the satellite. So basically, when the data are collected from the satellites, it comes down to one of our CDA stations, or it's processed into what we call the level 1B. It is then retransmitted up to the satellite, where that 1B signal is then broadcast. So the folks who really want that data in real time as fast as you can get their own antenna and bring down that GRP signal. We actually then capture the GRB signal at NSOF, where we turn that into our level 2 products and distribute it from that node. We're also broadcasting directly our DCS signal, the search and rescue signal, and a MWIN signal. So this is quite a complicated communication satellite as well. I know we've seen a lot of real pictures. Here's still the cartoon picture of it. Just to highlight where the instruments, so the Earth-facing platform, let's see, there we go. Down here at the lower end of the satellite facing the Earth is where the ABI and the lightning mapper are, so they can have a stable platform staring at the Earth. The telescopes look at the sun. We put out here in the solar array. Since we do actually get energy from the sun, it's nice to have something that's already pointing at it for those telescopes. The magnetometer is measuring such a very small signal that we have to get it away from the spacecraft. Because I actually was on a program that a body mounted a magnetometer in the 70s, and it was a great measurement of all the electronics turning on and off on the satellite, but it didn't very good of measuring the external environment. So you learn to put them out on booms so that you get away from the magnetic interference from the spacecraft. And then also the Space Environmental In-Situ suite is located at the upper end of the spacecraft. Now, stepping through, I only get to show you a picture because we have the great Tim Schmidt coming up, who's going to wow you with all the imagery and what the ABI can do. But as I already mentioned, this is a tripling of the number of channels, a quadrupling of the resolution, and a 5 times scanning. I like to say that we can look from the North Pole to the South Pole in 5 minutes, or zoom in on a specific mesoscale feature and update it every 30 seconds. So this is just a phenomenal instrument. As you can see from the picture, it's about the size of a washer-dryer combination in your house. And this instrument alone is bigger than many satellites that folks fly. And it sort of drives the whole system. Next, we've got our lightning mapper, and the great Dr. Steve Goodman is going to be talking about that. I was looking out here, I don't see him here yet. But that is a new instrument. It's basically a giant camera taking images in the band that will detect the lightning at the rate of every 5 nanoseconds, so for about 200 images every second that we compare with each other to really pick out the growth of the lightning. And I know he'll show some fascinating pictures of the various lightning thing. And as Joe mentioned, the potential of this is actually quite significant. And until we really start flying it and get the forecasters used to it and finding ways to really use these data, I don't know that we fully know what we can get from this. But Steve will have a lot more on that. Moving on to the space weather sensor, Bill Denning is going to talk about the space weather. I know, Bill, did you see the NPR press this morning? Yeah, well, it was great because NPR did a great piece on that this morning, and it was all about GOES-R contribution to space weather, and by the way, it did something with the Earth too. So I figured the space weather guys really got to love that. But you can see we actually have more space weather sensors on this satellite than Earth pointing sensors. So in the space weather community, I always say this is really your satellite that those atmospheric guys somehow have co-opted and getting all the press. So the first of this is the EXIS, which is basically 2 telescopes look at the sun. Simplistically, they're just measuring the irradiance, or basically the energy from the sun as it's hitting the Earth's environment. So that allows Bill, and he'll talk more about this, but to measure those solar variations that affect so many things here on Earth. Compared to today, this is just a much more sensitive instrument. In manufacturing this, one of the more fascinating things is this instrument has to be able to detect 7 orders of magnitude of different intensities. So if you can imagine building detectors to cover that incredible range of energy from very, very quiet things to massive storms without breaking, it's quite a technological feat. So you guys need to do some technology pieces on what's in these wonderful satellites. The SUVI is actually replacing the solar X-ray imager, primarily because the ultraviolet gives a little bit better definition of the surface of the sun. So again, the sensitivities are much more increased, and what it can pick up on the surface of the sun. Most interesting thing about building this sensor is that the filters on this are so sensitive that if you took one and dropped it from about a foot above the table and just dropped it, the air pressure in that distance would destroy the filter. So we're trying to build things that sensitive to be able to do the mission that is needed, while putting it on a giant monster like you see on the horizon here and launching it into space. So it's quite a technological feat to be able to do all that. The SEISS, just measuring the ions, electrons in a near-Earth environment to help with modeling the area around the Earth and improving a lot of the understanding of what's going on there. Again, Bill will get into the applications area. And the magnetometer at the boot, it's one of many magnetometers, trying to capture the whole magnetosphere of the Earth and really understand the variations in that for the space weather community. We get so excited about all the sensors, sometimes we forget to talk about all the other payloads on board. So we are flying, we're continuing to fly search and rescue detectors so that people that have the emergency beacons and get lost out in the woods, or their boat or airplane has a problem. The satellite will immediately pick up those beacons and relay it to the central control facility, who will get rescue workers out to do that. This year we had about 250 people saved by this system. With GOES-R, we'll have much more sensitive detectors to be able to pick up even fainter signals. The Weather Service also has an information network where they put various weather information and imagery and model output, and gives that out to emergency managers so they can have a direct link, sort of a low bandwidth capabilities. Many places it's a redundant system. In case of a disaster, they can still get critical weather information. We also are continuing the data collection system, increased capacity over the current GOES. Primarily, this is moving data from environmental platforms, such as, my favorite one is the river gauges. So the Weather Service, USGS, wanting to know the river heights. The data from all those river gauges are being bounced up to GOES and back down to those sites. So we provide that service. And I already mentioned the GOES-R rebroadcast. For those who want really low latency stuff, that we can get the data to them in just seconds if they build their own GRB antenna. If you look at all these components, as we were building this satellite, one of the Lockheed folks told me that this is the most complicated communications satellite that Lockheed Martin has ever built. Think about that. We think of it as a weather satellite, but it's the most complicated communication satellites ever built, just because of the incredible number of frequencies, the cross-banding, backing up the systems on the satellite in order for them to last 15 years. So when we were building it, trying to test all those paths and making sure they're not interfering with each other, and that was just an incredible challenge. Moving on to the ground system, I showed you the architecture. The primary sites, again, are at the NSOF, and then our CDA stations at Wallops and Fairmont. But just as a sense, people forget how it looks so easy to just show a few buildings and a few antennas, but this represents 1,100 servers, thinking of high-density processors spread over 5 geographic areas, about 5 million lines of code, 350 workstations to make this incredible system work. So a lot of work went into building this. This is about $1.5 billion investment in just the ground system to produce the products that you will all see in a very rapid fashion. I just put a list here of our baseline products that we've, this list was put together back in 2006. So obviously, as we've learned over time the value of this, we know that the products suite will expand, and we'll learn how to use this data much better. But these are basically continuation of the kind of products we see today, just much better with the capability of the GOES-R. I did want to mention that we have been working very closely with the Weather Service, so our scientists, our Weather Service compadres, have been working to really exploit how to use these data sets in operations. And to do that, we've actually flown product sets to the Weather Service that totally replicate the capability of GOES-R to get people really ready for it and learn how to use it. It's been a resounding success. The feedback I get has got folks very, very excited. You know, you heard a little bit from Joe, certainly in the National Weather Service, there's a lot of anticipation of this capability getting out to them. But it's not only served the purpose of getting ready for GOES-R, but we will continue to work through this proving ground with whatever users are interested, so that we can further exploit the data once the satellites launch. We can combine various, there's some exciting research going on, combining the lightning mapper with the imager, with radar, try to build integrated products to really improve the warning process. So there's a lot more to come. So I mentioned this is where I'm excited. This is our last couple of months have been pulling all this together and getting ready to launch. And as you saw today, we rolled it out to the pad, ready to hit that button for it to go. Once we get it going, it will take us about 18 days to get it fully up to geostationary orbit. We'll start doing our processing. We're already talking about, getting that first image out there and the press releases. Get on the list of getting that image out. Probably about 3 months in, we'll start seeing data flows, so the really sophisticated users can start using the experimental data sets. We will continue to validate that, but we'll have it on for a good year at that central test location, so that we can continue to flow the data and people can use it even though it's not in an operational state. I know you do a lot of outreach, so I got another video here.
Whoa! Things are looking pretty bad down there. But don't worry. I'm going to give weather forecasters a heads up and help you stay safe. I'm GOES-R. I'm a new weather satellite, and one of my jobs is to keep an eye on Earth's weather as I orbit above. But I'm 22,000 miles above Earth. How does your local weather forecaster know what I see all the way up here? First, I have to figure out what's going on. I point my special camera at the Earth and take pictures of the clouds I see below. My pictures show where the clouds are, but I also take lots of other notes about the clouds. For example, how high they reach into the atmosphere, how much rain they might cause, and when a severe storm may be forming. But I can't keep all of this information to myself. I have to share it with weather forecasters down on Earth. A big antenna is waiting for my call. Since I'm a satellite, I send my pictures and notes in a computer language of ones and zeros. Luckily, the antenna speaks my language. Computers connected to the antenna organize my notes and combine all of the pictures and cloud information and translate them into weather maps. They send a version of the maps back up to me. I'll hold on to these for later. Another copy of the maps is split into smaller pieces. This helps the maps move faster from one place to another. The map pieces are then sent for processing before being sent back up in the sky to a communication satellite. From there, the maps are picked up by antennas at the National Weather Service forecast offices in each region. There are more than 100 offices. I also take the maps that I received and send them out to companies that specialize in making the maps more colorful and better for viewing on TVs and computers. The colorful maps and the maps from the forecast offices then go to your local weather forecaster. The forecaster combines the information from these maps with lots of other information, like model forecast data and radar data, to make predictions about the upcoming weather in your area. And that's how I help you find out if bad weather is going to ruin your afternoon plans. You're welcome.
Yeah, I put that on there. Just I know that some of you do outreach to schools and stuff, and so our website and our YouTube do have a number of those very educationally focused things. We've been working with JPL in developing those. So today, that's about my level of understanding of it. So I think I'll end with that and lead you with if there's any questions. Since Joe did such a great job answering all my systems questions, maybe you're done.
For those of you who have questions, push the button. You don't have to get so close to the microphone. Don't overmodulate, because it'll go right through into the live stream and into the webinar as well. So please, let's open up the floor to questions for Greg.
I think we're working this mic, maybe. So we noticed most of these, Ricky Matthews, WCYB in Bristol, most of the ground systems are on the East Coast. Is there a primary reason for that, why they're located in Maryland and then other spots?
Traditionally, we've had it at Wallops from the early 70s. Proximity and communication were very expensive, so that's what we did. When we had to do the backup, we actually looked geographically because we were thinking there might be some better places that would like to have direct downlinks. But from geostationary, our data downlink is done in the X-band, and so the footprint of the antenna is actually very, very small. So when we're staring at Wallops, you needed to be in the footprint of the X-band with sufficient power to not get giant antennas. So it sort of limited us to a relatively small area. And so we did optimization up and down the East Coast. And the nice thing in West Virginia with the mountains and stuff, you can get on different power grids and you can get the shielding. It's a nice quiet area. So there was a lot of factors in that decision. I haven't been asked that question in a long time. Thanks. Very good. Well, look forward to all the experts talking about all the applications.
Jennifer?
Jen Carfagno from the Weather Channel. I know we're just launching this tomorrow, but I know you also said that this is 20 plus years in the making. Are you guys already starting to think about the next series?
Yes, there is a group who is actually doing architectural stuff to think about how to take advantage of, as technology advances, small satellites and intercommunication of satellites. Because one of the things when you spend so long to build a big complex like this, it takes so long, and as Tim reminds me about every other week, you don't get to advance the technology very much. We're building 4 of these, which are going to cover 20 years. So, we got to find ways to get technology up faster by more robust architectures and different things. So that's being looked at right now. It's always exciting.